Hi, good evening all. Welcome to that week 4 open session. So, actually, just when you compare with that week 3 and week 4, yeah, may audible? Hello.
Yes, sir.
Cool. So, up to the week 3, whatever the data structures you have worked is that linear data structure. So, the linear data structures are very simple. They are traversing from first node to second node to third node if it is linked list. If it is array, they are going to be traversed using index positions. If it is stack, it is always one direction of input and same direction of output, that is push and pop. When it comes to the queue, we have always entering into the queue operation, which is always it is rear of the queue, and removing the element is always dequeue operation, which is from the front of the queue. So these are all linear. When it comes to that week 4, it is non-linear data structure. So actually week 4, week 5, week 6, keep going up to I think week 7. These things are non-linear data structures. So when it comes to the week 4, it's a non-linear data structure. They introduce the graph. So the graph is a collection of vertices and collection of edges. So in this graphs, we have directional graphs and undirected graphs are there. So these things you learned it. And the basic algorithms of the graph we have worked so far is that DFS and BFS, depth first search and breadth first search. And using depth first search and breadth first search, some applications we do. And additional algorithm, if you just you recollect and recap, is that some additional algorithms like in the DFS and BFS and tag, which is topological sorting. So this is the algorithm, standard algorithms which you understood from the week 4. Can you just check your live coding problems of the week 4? Are you able to access? Hello. In the week 4,
Yes, sir.
Yes, sir.
just a minute. I hope my screen is visible.
Yes, sir. Three.
Yes.
Yes, sir.
Lines, line to access. Yeah. Week 4. Yeah, it is the first problem. Yes. So hope my screen is visible. Is it right?
Yes, sir.
So let me just we understand what a problem statement is. Express time that is provided with the adjacency list. Adjacency list means maybe 0th station connected to which particular station. That is called adjacency list. You could see that adjacency list here. So that is 0th vertex is connected to 8th vertex. 8th vertex is connected to 0 and 9, something like that. So here you have to find a route from a start and end with minimum number of possible. So we are trying to connect that from a starting vertex to ending vertex. Here starting vertex is called as starting station. Ending vertex is called ending station because they are saying it is express time. The story changed. They are trying to change the story. We have to write a min hop function, sorry, minimum hop. So which you can say that minimum number of connected vertices, what you call, connected stations, what you call. So which it is taking adjacency list as a parameter, start station, end station as a parameter, to return that the cities to be visited from a starting and ending of it, from the starting to ending, to reach from starting to ending, what are the various stations it is connected. So that we have to find out that which is that minimum number. So actually we have many ways to reach from starting to end, but we are trying to find out that minimum halts, what you call minimum stations, that we want to find out. Return list with only the start. So if the end is not accessible, for example, the ending station is not reachable, maybe sometimes there is a graph which you are trying to traverse from a station 1 to station 8, but there is no connection between station 1 and 8. So then what you have to return is simply we have to return that start, only the start, because you have to have that staying of the same station only. There is no reachability for the ending station. So do you understand the problem statement? What exactly is this? Hello. Hello.
Yes, sir.
Now, so any particular approach do you have? Just you can speak out. Do you have any idea what algorithm it is preferred here? What is your approach? Do you have any idea of it? Just you look at the question statement and you look at that some prefixed code is given to you. Some prefixed code is already given. Just you look at a while and then you think about it. I think some graph also given. Yes. Of course, it is a directional graph. Sometimes they are using two directions. I think it is 1 and 3. They are using two directions. Some places they are using only one place. Actually, they are using 1 to 3. There is a adjacency. Is there 3 to 1? There is
So
adjacency.
0 to 8 also, sir.
Yeah, it is. Yeah, 0 to 8, 8 to 0. Yes, correct. Yeah. So anyway, just you look at this code and how this particular prefixed code will help you and how you are going to solve this one. Just any idea? Just let me discuss them before I'll start discussion. Any particular approach you have? Any idea of it? Please kindly speak out. Okay, so let me go with one kind of what is happening for that existing prefix code. Do you believe this particular code, is it BFS traversal? Is it
Yes, sir.
BFS traversal? Is it that? Hello? Hello?
Yes, sir.
So if you could see that, maybe in your existing BFS code, just let me open that. Maybe in your GitHub notes, you can find the BFS traversal is there. So maybe it is a directed, undirected, it no problem. Graph traversal algorithms. There is a BFSL, there is a list they are using. What it is returning is, it is either widgeted or not, it is returning true. True means it is widgeted. But I don't want this. Maybe some other things may be useful for us. Yeah, this is what, please look at. Finding the parent of a vertex using BFS. This is one of the, using the BFS algorithm to find the parent of the any vertex. That is what object of it. What is this one is returning is widgeted dictionary you are getting, parent information you are getting. Is it right? Is it right?
Yes, sir.
Similar way, if you just you see the extension of the BFS, level number also you can find out. Each particular vertex, it belongs to which level you are getting. Maybe they are using this particular same kind of code. This BFS list path level is there, no? I think the same it is used. Is it right? Is it right? Hello?
Yes, sir.
Finally, what it is returning is the level numbers it is returning, parent information it is returning. Now let me show you one particular graph, how it is this particular prefixed code is working. The prefixed code is there, no? How it is working, I will show you with some kind of a simple graph. So this is my graph, maybe 0, I'm taking maybe 1, it could be 2. Is my screen visible what I'm drawing?
Yes, sir.
3, maybe it is 4, and I'm taking 5. Maybe it is a simple or complex graph. Maybe I'm using a directional graph only because In the example, they used a directional graph. So I'll use that directional graph only. So this 3 might be connected to 1. Maybe 0 we are connecting to 4. And 5 we are connecting to 4. So sometimes I'll give 2 directions also because they are using it. So this I'm connecting to, we are connecting to 3. And this 4, yeah, 4 I'm connecting to 3, maybe something like this. So here, if this particular prefixed code, if I'm applying on this graph, so we are getting that 2 things returning from this function. Is it right? The level information, parent information. Is it right?
Yes, sir.
Is it right? Hello?
Yes, sir.
Fine.
Yes, sir.
So level information you are getting, parent information you are getting. Let's start our traversal from the starting vertex or origin of the particular any vertex. You can start that PFS algorithm. So I'll use it. The starting vertex is 2. Is it okay? So I can start it from any vertex, no? So now what happens, the level information you are getting by this particular prefix code. So what is my level information I'm getting is, so that 2, the vertex 2, it belongs to which level? Because it is that, 0th level. Am I right there? Is it right? Is it right?
Okay. Yes, sir.
So now, after this 2 is over, DFS, what it will do, the next level complete adjacents are going to be traversed. So what it is going to traverse? This one and this one. Is it right?
Yes, sir.
Now, what is the level number of the 0th vertex?
1.
Yes. So what is the level number of 3?
1.
Yes. Good. So now this is over. After that, one adjacents you are checking. So what are the one adjacents it is checking is, sorry, 0th one adjacents, I'm sorry. 0th one adjacents it is checking. So 0th one adjacents are, we are having 1 and 4. Is it right?
Yes, sir.
Yes, sir.
So
Sir, 2
immediately, oh, two also there, of course. Of course, 2 is already, it is traversed, no, it doesn't traverse again. Is it right? Because visited is 2 means it doesn't traverse. Is it right?
But sir, it can go again now back.
No. There is a condition, please check it. It's not visited only, it will traverse. Is it right or wrong?
Yes, sir.
Yes, sir.
Clear? That's it. So that is a basic condition whenever the PFS it is working. Now, so after this 0 is over, 3 is over, then 0, 2 adjacents are going to be traversed. So what is the level information of 1 and 4? 1 it belongs to which level?
2.
4 it belongs to which level?
2.
Next level. Is it right?
Yes,
These
sir.
2 are going to be the second level. So this is 2, this is 2. Is it right? Is it right?
Yes, sir.
Next one. So after that, so 4 is not having any adjacents because 4 is having incoming degree, but it is not having outgoing. But 1 is having outgoing. Is it right?
Yes, sir.
So that what is adjacent to 1 means only 5. So 5 is going to be traversed. So what is its level information?
3.
Very good. This is that first return value we are getting from this. This is what the level information you are getting. Is it right? Is it right?
Yes, sir.
So even you can check your existing code. See, you are getting is 0 and its level, first vertex and its level, second vertex and its level, third vertex its level, fourth vertex its level. Up to this, is it clear?
Yes, sir.
Now I'm getting that second information, parent information also you are getting. Parent information also we are getting as a dictionary. Is it right? Sorry.
Yes, sir.
So who is the parent of the second vertex, vertex 2?
0.
Nobody
Zero.
is there.
No,
Either
no.
you can, no,
Nobody.
you can represent
Minus.
with 0 or -1, no problem. Anything is okay.
Yes, sir.
Yes.
So let it be that -1 because 0 is available value is there. Let us consider it is a -1. Is it okay?
Yes,
Sir, I did
yes,
not
sir.
get it.
Root is not having any parent. Then it should have some kind of remarkable value. Is it right?
Okay.
So root never have the parent. So how the root parent is represented with -1. Clear? Clear? Hello.
Yes, sir.
So
Yes,
this is
sir.
over. Next one. The parent information for 0th vertex. Who is the parent of 0?
2,
Very good. Who is the parent of this 3?
2,
Yes, very good. Who is the parent of this 1?
0.
Yes, because it is the next level we are going, it is 0. So parent of this 1 is 0. Next one.
But
So the
sir, 3 also is there. So
no, who is the 3? One's parent I'm asking. One is traversed through 1, 0 or 3?
okay.
Tell me.
0. Through
Hmm.
0 we will
So
traverse.
that the parent of 1 is 0. Next one. The parent of 4, can you tell me?
0.
Yes, 0.
0
The,
and 5.
no, 0 and 5, how it is? See, once 0 is traversed, its complete adjacents are traversed first. It's a BFS. Is it clear?
Yeah.
Yes.
So all adjacents of 0 is finished. Then only it goes to the next level. Is it right?
Yes,
So
sir.
Yes,
that
sir.
the parent of 4 is 0. Next one. The last one is that the parent of 5 is what?
2.
1.
1. The parent of 5
1.
is
Yes, sir.
1. Now, here we got the parent information. Is it right?
Yes, sir.
We got
Yes,
the
sir.
parent information. No? Then our simple logic is we got that level data, we got the parent information with already prefixed code. Whatever prefixed code is provided for you, the prefixed code is returning some data for you. The data we got it is the level number we got it, and at the same time the parent of each node we are getting. Now our job is a simple kind of logic we need to uh, chalk it out. What is the simple logic? Very simple logic. Traverse the parent dictionary. The parent dictionary. This is the parent dictionary. No, is it right?
Yes, sir.
This parent dictionary in back traverse, back traverse, back traverse from end to start. What do you say? End to start. Is it clear? For example, I want to find out the route from start is that station 2, end is that 5. Is it okay? Is it okay?
Yes, sir.
Okay.
Then we try to traverse from end to start. So I know who is the parent of 5. Is it right?
Yes,
Yes.
sir.
Then what happens? Example, I've taken the source is 2, end is 5. So what I'll do is first I'll go for 5 to 1. Who is the parent of 1?
2.
3.
Sorry.
Who is the parent
0.
of 1?
0, 0,
0.
0.
0. Who is the parent of 0?
2.
2.
2.
So this list we are going to return by your min-hops function. The list what you are getting is maybe 5, 1, 0, 2. So simply we return this one. This one we are returning. Hope you understand. Is it clear?
Yes, sir.
So that the min-hop function what you are talking out is the return values level information is there, parent information is there, that is returned by already prefixed code, which is the prefixed code is this, and using it you have to figure out a back traversing from end to start, not from start to end, because end knows who is the parent of it. Again, the parent of that, each one we are traversing it.
Sir,
Hmm.
why 3 is not parent of 1?
Why?
3 is not parent of
See, let me tell you that you started from 2, is it right?
Yes, sir.
Maybe you traverse 0 and 3, is it right? Adjacents of the 2.
Yes, sir.
If 3 is traversed, for example, before 0, clear?
Yes.
Then what happens, 1 is traversed, but
Yes.
only 1, is it right?
Yes, sir.
After 1 is traversed, Is it possible the adjacent of 1 is 0? No. Clear? Clear?
No, sir.
After 3 is traversed, what should be traversed? Please tell me.
After 3 is traverse, 1. 3 will
1.
go to 1.
1 is having only one adjacent, 5. Is it right?
Yes, sir.
Then that is also one path. That is because, see, one graph is not having only one BFS output. Is it right?
Yes.
Multiple BFS
Yeah.
outputs are there. Yeah.
Yes.
This
Yes.
is one way I am telling you. Here.
So, sir, our output can also be like 2, 3, 5.
That's what the thing. We are returning a list. Maybe you have that another path also. Clear?
Okay, sir.
Another path also. Maybe you whatever you said it is right. Maybe the parent information you are getting is as per your thing. I'm going is 2 is having parent information is -1. After 2, it is gone for 3, not for 0. 3 is having only one adjacent, that is 3. 3's parent is 2. Is it right?
Yes, sir.
Then 1 is traversed. 1's parent is 3. Is it right?
Yes, sir.
So after 1 is traversed, 5 is traversed. So 5's parent is what?
Yes, sir.
5's parent is who? Who is the 5 parent?
1.
1.
1. Very good. So after 5 is traversed, only one adjacent is there for the 5. That is 4. 4's parent is
5.
very good.
5.
So up to this, it's over, no? Anything pending?
Nothing.
Fine.
So 0.
So, oh, sorry, 0 is missing, no?
Yeah. Actually,
Okay.
230 it should be like that.
Oh, okay. Sorry. After 3, 2 is over. 2, 0 also can be traversed, okay? This 0 can be traversed. Is it right? Fine.
Yes, sir.
Fine, no problem. But the 3 is used for next level. I'm not using 0. Is it okay?
Yes, sir.
Now, same starting and ending is same. I don't want to change it. Is it right?
Yes, sir.
Now, the path we are getting is, that means ending to start. My ending vertex is 5. So that 5 parent is what?
1.
5's parent is what? 1.
1.
So 1. 1's parent is what?
3.
Yes. 3's parent is what?
2.
Over. So what is this length of this list?
4.
So this length of the list.
4.
So that we are returning maybe another path also. Is it right?
Yes, sir.
So, but interesting way is, if you could look at the min-hop function, what you are returning is the result we are getting is the list of that vertices. Is it right?
Yes, sir.
So what they are doing, length of the shortest path they are getting. No worries, no. Either this path or that path, the length is 4. Is it right?
Yes, sir.
So that if you could check it test case also, the output is what they are doing, the length of the vertices. The path vertices is then the length they are returning. Is it right?
Yes, sir.
So that no worries, even it is a different BFS traversal, it will do. Multiple BFS will get it, but we are getting only length of it, because BFS traversal for one graph is only one traversal is there. Maybe multiple traversals are there. Only thing is, finally we are getting the length only. Is it okay then?
Yes, sir. Understood.
So now you need to implement the min-hop function. The min-hop function has to do back traversal. Is it right? End to start. Okay.
Okay, sir.
Hello. Yeah.
Yes, sir.
So whatever the return results of level information, parent information is there, please use it and do the backward traversal and implement the code. Just I'm giving you just a 15 minutes of time. Just quickly you write the function that is there, the min hops, which it is taking that, as per that it is taking adjacency list as a parameter, start vertex and end vertex. Implement your code, write your code here. But you supposed to use this existing function. Whatever return values you are getting is level information, parent information. Use it and write your code. Yeah, start writing. So I'm just, it is the rough diagram which I've shown you that it is available on the screen for an idea. You figure out only that min hops. I think min hops is a simple function where just it is backward traversal you need to do. So now it is 8:30, 8:45. We'll get back. Somebody asking if I find all possible path, return min. So actually, whenever BFS traversal we are getting is the paths we are getting is that multiple paths we are getting. Actually the multiple paths in the sense most possibly all of them are same because each level we are finishing, no, mostly all of them are having the equal length only. Don't worry about that minimum. Always it is going to be the minimum only. I think Vicky is asking about this. Mostly we are getting each level we are finishing it. We are going level by level. Either you are going from left to right or right to left is not an issue. But definitely we'll get it. One is a minimum one, not an issue. Don't worry that again you have to use min function. So I think some private test cases failing means did you check the condition? I think there is a edge case. Vicky, I think if you are not able to speak out, you can check it. See, return a list. Sorry, return a list with only one start. For example, there is no reachability. Ending maybe graph is like this. Maybe the graph is like this. You are trying to reach from 2, 3, 4. So we are trying to have this graph is like this. Maybe you have like this. Your started is here, your ended is here. Then what happens this? You cannot reach from starting station to ending station. Am I right or wrong? Hello?
Yes.
So then you suppose to return only 2 as a single item. So this length of this one is the edge case. I think it is edge case is there. Yes. See, look at here. There is no reachability from 8 to 0. So that what you are getting is just it is length of that 8 you are getting is 1. Because 8 is considered as a list. Vertex 8, length is 1. So that is a one edge case you need to check it. Okay, that edge case we can include as a simple if condition, not an issue. Hope you understand what is the edge cases. Yeah.
Sir, you are not audible.
Yes, tell me. Hello.
Sir, you are explaining.
No, I'm not explaining. Just I'm giving you just 10. It is scrolling actually to make it visible.
Okay, sir.
Yeah, any of you have been figured out? Just can you paste the code in the chat box, the message box? Any of you done so far? The min hops. No, Vicky, actually, I think you can paste it, but I need your explanation also because how did you figure out? Maybe your mic is not working. Somebody else other than Vicky? Somebody
Just a
else?
minute, sir.
Yeah, it's okay, Sri. even somebody figured out the partial code also, no issue. Maybe lively we can try and fix the errors. Maybe we can paste it here. Some edge cases is there. We'll chart out the solution.
Yes, sir. One of the edge cases is when
Yeah,
you
you
start
can
in.
paste it. You can paste it. We'll figure out that. Yeah, that's okay. We can understood that what you are trying to say that, but I'm trying to see somebody's code, like any of you. Wiki, other than because your code is already fixed. That's what I don't want your code. Sri, you want to paste something here?
Yes, sir. I just figure out the edge case. That will I.
Okay,
Yes, sir.
okay. Yeah,
That
you
I'll
paste
pick.
it. You paste it here.
Yes, sir. Just a second, sir.
Okay. Other than Sri, anybody has done? Yes. Can you? Disha, you have done anything so far? Anurag, Dhanvantari, yeah. I think Sri has pasted something. No, no.
Yes, sir.
Why,
I DQ'd the.
no. Why you are using DQ all this stuff? Already it is done by everything done by the BFS traversal. No? Is it right?
Oh, yes, sir. Okay.
Everything is done by that BFS list path. Just you have to call that function and use it. See,
Yes,
very
sir.
simple. Just let me open this. Is my code editor is visible?
Yes, sir.
Just a minute. Yes. See here, already this particular function is doing everything like using the queue, pushing and popping. Just you check it, appending, popping. Is it right?
Yes, sir. Okay.
I don't worry about it. Just I have to do that, getting the level information and parent information by calling that above function. My function is already available, BFS level path, which it takes that adjacency list, starting, ending. Is it right?
Yes, sir.
The two returned values we got it. See,
Sir, it
everybody-
only takes one parameter, start or end, not both, sir.
Okay, sorry, I'm sorry. Start only. Takes only start, no? Yes. It takes only starter. Correct, right. So we are getting that level information, parent information, 2 dictionaries. Is it right?
Yes, sir. Through BFS.
Yes, through BFS. So
Okay.
whatever just I have discussed this kind of thing, this level
Yes, sir.
information, parent information. So here,
Mm.
right now, I'm not worrying about edge case. I want to return that result in back traversal. Is it right?
Yes, sir. From
So
end to
yeah,
start.
it is. So that let me take that result is a one empty list. Forget about the edge case. Let me do that first. So what I'm trying to do is I'm trying to back traverse from that last to end. So what I do is result dot append is first I'm appending end vertex. Is it right?
Hmm. Yes,
Because as per this one, I've written 5 1 3 2. Is it right?
yes, sir.
Similar way 5 1 0 2. So that I want to append it into the result. So maybe that is a temporary list. In that list, first end is going to be appended. So what I'll do is I will try to do a complete loop until I reach to the start. So that while my result or whatever added recently, maybe recently added is the -1 because last element we can detect it with -1. Is it right?
Yes, sir.
It is not equal to starter because we are traversing from back to starter. Fine. Fine.
Yes, sir.
So until our result recent added one is reached to start, we are trying to repeat a loop. In this loop, what I'll get it is I'll get a parent information that is parent of the recently added end. Clear? Now, so result dot append is whatever that end which is added, the parent which you got it, again you are appending into the result. Fine.
Yes, sir. Got it.
So finally, what I supposed to return is result. Up to this, is it clear, everybody? Hello.
Sir,
Yes,
please
sir.
repeat once again.
See, already we have a particular dictionary, this parent information. Is it right?
Yes, sir.
In this parent information, first we are getting that. So first we are getting that. So these two informations you are getting through this function. Already this function is giving you 2 dictionaries. Is it right? For any graph. Now first what I'm doing is the parent of end I'm getting. So parent of this parent of end. So end is there. This it is appended into result list. This result is an empty list. It is appended with 5. Is it right?
Yes, sir.
So then we try to repeat a loop until we reach to the start. Whatever recently appended one, it is reached to start. So my recently appended one is what? 5. Is it start one?
No.
So no. So no worries, it enters into the loop. In this loop, what I'm doing is the parent of end I'm getting. What is the parent of end? What is the parent of this end? What is the parent of this my end? 5.
1.
1. So
One.
that 1 is going to be appended. Is it right? Because we are getting p equal to the parent of end you are getting. We are appending result dot append is parent. Fine. Okay.
Yes, sir.
Now again this loop is repeated. Now what is recently added? 1. Is it right? Is it
Yes,
right?
sir.
Does one is start? My start I have given is 2. My end I have given is 5. Is it right? Is this 1 is equal to 2?
No.
No. So again loop is repeated. Who is the parent of 1?
0.
So that we are getting the parent information. The parent of this particular, oh sorry, maybe end is not right. The parent of the recently added one, no, I'm sorry. The parent of recently added one, which is going to be -1. Is it right?
Yes, sir.
Okay. The recently added one is what? Hello?
How it's -1?
Recently added one, no? What is the recently added one in the list?
Okay.
What is the parent of 1?
Sir, then
Minus.
it needs to be result -1, right?
Result -1. Oh, sorry, I'm
No,
sorry.
it's just written -1. Yeah.
Correct. Yes. Result minus 1. Wait. I'm sorry.
Parent of result minus.
Yes, parent of
Parent
result
of-
minus 1. Yes, correct. Perfect. Perfect.
Yeah.
Now it's perfect. Clear? Okay.
Like, can we do it like end equals parent end? Is that right?
End equal to? Yeah, it's okay. Updating that end equal to parent end. That is also okay. Now the recent end is updated with this. Now what should I update here? End. Is it right? Hello?
Yes, sir.
Yeah,
Is this all right?
So
This is fine, no?
I got the
Hello?
26th line, but the 27th line I'm not getting it. Can you please
No.
explain?
So
I
what
got
is the
it
recently? No, wait. Let me complete. Please wait.
Okay, sir.
First, it is adding of that first end 5 before entering into the while loop. Is it right? Is it okay?
Yes, sir, yes, sir.
After that, result of recently added. What is my result? It contains 5. Clear?
Yes, sir.
Is it start 1?
No.
No. So then it enters into the loop. Is it right?
Yes, sir.
So now the parent of end is there. That is updated into end. What is my parent of this end? This parent of this end. Sorry. Yeah. This parent of this end is what?
1.
1. So now the recent end is updated with 1. Is it right?
Yes, sir.
So that is appended into list. Clear?
Yes,
List
sir.
result. Clear?
Yes, sir.
So 1 is appended. Again, what happened? This loop is repeated. Once this loop is repeated, what is recently added? This is 1. Last element. Minus 1 means what? Last element of the list. Fine. Now, what is the parent of this one?
0.
So
0.
this end is updated with 0. Is it right?
Yes, sir. Got it.
Yes.
It is added here. Clear? Now, is it start? No.
No.
So that loop is repeated one more time.
Sir, I had a
Hmm.
question.
Hmm.
Like, in this function, if we make the parent list,
Hmm.
it's giving -1 for 0.
No, no. Parent list is not that. Parent is a dictionary. Is it right?
Yeah, sorry. For the dictionary,
Hmm.
the entry for 0
I'm
is
not
-1.
using parent of -1. No, I'm using parent of end.
Yeah. So like, the end is 0 here, right? In
No,
the
end is not 0.
example test case.
No, no. End is
Yes.
0. No problem. No
In the
problem.
test case.
Test case, no problem. Because you have the vertices 0 to 8.
Yeah.
No problem. Clear?
Okay.
Okay then. So maybe you have the graph is like this. You have the graph is this. The end they have given this. The start they have given like this. Is it okay? No. Fine. Hello.
Okay.
Fine. So that's not issue. Now after reaching this 0, and then we are adding that 0th parent is what? What is the 0th parent?
2.
What is 0th parent?
2.
2. 2 is added because end is updated and it is added. After adding, does my last element is start or not? Is it start?
Yes.
This condition is failed means this loop is stopped. This loop is stopped means we are returning the result. Is it right? Is it right?
Yes, sir.
But there is a failure. For example, this. If there is no reachability, you suppose to return that start vertex as a list. Is it right? Is it right? Hello? See, there is edge case they have given, no, in the question.
Yeah.
See,
The test case is the edge case, right? The first
you have
test
tried
case.
to, yeah, it is. The return the list with only one start if the end is not reachable. For example, already I have shown you this. This is one example. 4 is not reachable. Is it right?
Mm.
Whenever 4 is not reachable, can you tell me the parent dictionary what it returns? My parent information of, for example, I started from the start is 2. The parent of start is the parent of, because nobody parent is there. It is having -1. Is it right?
Yes, sir.
Fine. So the parent of 3 is what?
2.
Yes, very good. The parent of 4, any parent is there for the 4? No.
9.
Still it is -1, is it right?
Yes.
So that please check your initial value. See, look at here. Initially what it contains, all of them.
-1.
If they are reached, they will be updated with other than -1. If they are not reached, they still remains -1. Is it right?
Yes, sir.
Now, can I put one edge case condition here? What is my edge case condition is, if my parent information of end is -1, that means there is no reachability. Hello, everybody seeing there?
Yes, sir.
If my parent information of my end is -1 means it is not having any parent. If it is not having any parent, there is no reachability. Then what do you return is, just return the particular start as a simple list. They said it is return the start vertex as a list. That is what we are doing. Is it clear? Hello? This is a edge case whenever there is no reachability. If no reachability to end. How do you know that reachability is not there for the end? Is either level number is -1 or parent information of the end is -1. Clear? If this condition is not satisfied, means the parent is of the end is that some parent is there. Some parent is there means through the parent I can traverse to end. Is it right? Hello? Hello?
Sir, where
Yes,
are
sir.
we?
Yes, sir.
Yeah. Somebody asking there.
Sir, where are we checking reachability? Like if parent.
This is what, no? Parent of end. See, what is my dictionary it contains? Please tell me.
Sir, parent and level.
Parent and level. My parent information is -1 is there. Level information also -1 is there initially. Is it right?
Yes, sir.
My level information of 2 is this graph I am saying about. What is my level information of this 2?
0.
Fine, very good. What is my level information of 3?
1.
Very good. What is my level information of 4?
2.
No, there is no reachability, no.
No reachability.
So
Yes.
that this is 1, but level information of this 4 is -1.
-1.
So
Yes.
that if there is no reachability, either level information or parent information of my end is -1, it exists.
Yes, sir. Okay, sir.
This edge case we can check either using this particular, either this -1 or level of end -1, I can check it.
Understood, sir.
Clear? Yeah. Somebody asking something? Somebody raise your hand. Shall we run this now?
Yes, sir. I had a question. Like,
Hmm.
what if, like, it's a separate group of 3?
Hmm.
Like, it can be reached, the end
Hmm.
can be reached, but not from the start.
Yes. Fine. You said is right. For example, you have a particular one. This is a start. This is 3, 4, maybe 5, something like this. So it is reachable from the 5. Clear? This 4 is reachable from the 5. Okay. But what happens, through the 5 you are reachable. Fine. Is it right?
Yes, sir.
So is there any reachability for that 4 other than this 5? No possibility. Again, I'll do the reverse edge here. Maybe, not from 3 to 4. I'm giving 4 to 3. Is it okay? Is it okay?
Yes, sir. Yes, sir. Yeah.
In this case also same, in this case also you have, what happens, the level information of this one is 0. The level information of this is updated with 1. Clear? Hello?
Yes, sir.
But the level information of this 5, because whenever start is chosen is this, the level information of 5 is still remains -1. Is it right?
Yes, sir.
Hello?
Like, the if statement that we have added, it won't show this, right?
No. I'm telling about level information. Then I'll talk about
Yeah, yeah,
parent
yeah.
also.
Okay.
Fine. Next, the level information of 4 is still -1. Clear? Now let's go with parent information also. The parent information of this, no parent is available, -1 is there. The parent information of this one is 0. Is it right? Hello?
Yes, sir.
So the parent
Yes.
information of 5. So first 5 is not reachable from anybody from the starter. So that still the parent information of this 5 is -1 only. Clear? Hello?
Yes,
Yes, sir.
sir.
Yes, sir.
So here it is -1. There is no reachability. There is no level. Clear? Either you can use level information is -1 also. You can return that just start vertex as a list. Or either my parent information of the particular end is not reachable through any of that from the start. Maybe somebody else it is reachable, but through start it is not reachable. Is it right?
So like that's why we have been given two
Exactly.
lists, right?
Exactly.
Level and parent.
Yes. 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 Okay. So now let's run it. Hello. Shall I run it?
Yes, sir.
Yes, sir.
Just- I think this edge case also works now. Maybe somebody else used that level information also. That is your choice. Yeah, it is 3. This edge case all satisfied. Submit the inner test cases. Mostly this is same because as simple as it, because only most of the job is done by this. Only we do the backtracking. We have to figure out that from ending vertex to start vertex whether it is you are able to traverse. If you are able to traverse it, this particular loop it works. If there is no reachability, simply we have only one statement. This particular end is not reachable through the start vertex. Maybe some other station is connected, but our express train starts from a start vertex. There is no connection between that start station to end station. Maybe in between intermediate station is that is connected to end, but that is not the scope of the start vertex. Is it right? Hello? Hello?
Okay,
Yes,
sir.
sir.
Yeah. This is one. And the next problem. Kindly open the next problem. Yeah, this is. Let me read the question first to understand. So, writing a function that is back forth, which it is taking that maybe it is similar to that, the same. I think so. Back forth, back and forth, which it takes that adjacency list as a parameter and end one as a parameter and end two as a parameter. It returns that maximum number of possible routes, okay, from the node or vertex end1 to end2. Oh, they have taken it is clearly undirected graph. Why they are taking undirected graph is it is not a restricted graph. You can traverse from any vertex to any direction. That is called undirected graph. So without going through that same node again, exception to end1 end2, yeah, it is good. So intermediate nodes cannot be repeated in that path. So I'll show you that what is really happening. Let me see the graph also what they have given. So the connectivity details between the nodes are provided in the adjacency list. See, the 0 is connected to 2, 3, 6. And if you could see that vertex 2, it is having that 0, 3, 4. See, 0 is connected to 2, 2 is connected to 0. Hope you understand what does it mean, because it's undirected graph. Is it right? Is it right? Hello?
Yes, sir.
Yes, sir.
2 is connected to 3 and 4, 3 is connected to 4 and 2, so that it is undirected graph. We are trying to connect between end 0 and end 1 and end 2. They have given that end 1 is 0. Of course it is like a start and end only, but they have changed the names are end 1 and end 2. So here the output it is getting 3. Let me see that what are the different ways of traversing. So this is the graph. If you consider, maybe I'll just quickly go for the graph. So what is happening? The maximum number of possible paths between that end 1 and end 2 without repeating that intermediate vertices. So let you see that. Maybe the graph. I have a look of that. Let's have that 5, 6, 3, 4, 0. Yeah, 0 is started from bottom. Let me start in that way only. So the 5 is here, 4 and the 6, and this is 3 and 2 and 0. I think they have given it's 1. So they have connected 4 and 5, 3 and 4. I think 2 and 3 is sure. This is sure. Let me check it once. Yeah, it is 6 and 0, 1 and 6. 6 and 0, 1 and 6, 5 and 6 also it's there.
Sir, 5 and 1 also.
Yeah, 5 and 1 also there. Okay. 5 and 1 also there. So I
1,
think,
3 and 0, 3.
yeah, 1, 3 and 0, 3 also there. Maybe something like this. Yeah, it is the graph. I think so. Almost it is the same.
Sir, 2, 4 also.
2, 4. Okay. Sorry. 2 and 4 also. Yes. Yeah, this is our graph. We are trying to find out that. So frankly speaking, it is finding number of unique paths. I can say that unique paths. Why do I say the unique paths is between end 1 and end 2. End 1 and end 2. Let me show you that what is my end 1 and end 2. Maybe end 1 they have given is 0 and 1. Yeah. So here end 1 they have given us 0, end 2 is 1. See, look at here. So we want to find out that number of unique paths. So can you investigate what are the different paths are available and what algorithm it is suitable? Maybe you can look at your prefixed code also. What algorithm is suitable to do this job? To reach from end 1 to end 2. What algorithm they are using?
DFS.
DFS. So why do you use DFS, depth first search? When do you use depth first search? See, when do you use depth first search? When do you use breadth first search?
Oh, sir.
So BFS is for the shortest path. As I
DFS for?
the longest one. I
Yes,
think.
it is longest path.
Longest path.
So whenever you want to find out that longest traversal, like you are going depth, longest number of edges number of vertices you are increasing in depth. So that is called longest. So BFS always prefer for the shortest. So that here we want to find out the different paths. So maybe many adjacents are there for end 1. We try to traverse via adjacent 1, via adjacent 2, via adjacent 3, something like that. So here BFS is preferred, I think. Is it right? For example, if you are going by DFS, what I supposed to go is, I have to go for 0 to 2. Is it right? Hello?
Yes, sir.
Then 2 to 3. Is it right?
Yes,
Yes,
sir.
sir.
Then 3 to 4. Something like this. Then 4 to 5. Is it right?
Yes, sir.
Yes.
Then maybe 5 to 6 I might go. 5 to 1 I can go. Let us consider the depth only, first depth only, 5 to 6. After that 6 to 1. Is it right?
Yes, sir.
Otherwise, if you go 5 to 1 and 1 to 6, is it okay? That is called depth first search. I think depth first search is not at all useful. Clear? Now, can you tell me the BFS different unique paths to reach from end 1 to end 2? Unique paths. Make sure it is unique path.
So 130.
The first one is 0 to
2.
1 is I started from this, that is 0 to
0 to
3, 0
0
to
to 3.
3 to 1.
1.
This is
1.
the first path. Maybe something like 0, 3, 1. Is it right?
Yes, sir.
This is the path 1. See, unique path means, see, they clearly said in the question statement, I think, the connectivity between end 1 and end 2, exception for end 1 and end 2, without going through the same node again and again. Is it right? Unique
Yes,
path
sir.
means except end 1 and end 2, intermediate vertices should not be repeated. That's the case. Hope you understand. Hello?
Yes, sir.
Now, so this path is over. The next path we are finding, path number 2. So path number 2, can you tell me what is the path number 2 possible path? End 1 to end 2?
0, 2, 3, 4,
Sir,
5, 6.
061.
0, 2, then 0, 2,
4, 5, 6, 1.
4, 4, then
5, 6, 1.
5, then 6, then it is 1. Maybe it is 0, 2, please make sure not repeating 3, 4, and then
5 and 1, sir.
5, 6, 1 said somebody.
No, we can have 5 also and 5, 6, 1 also.
Why do you use 5, 6, 1 is wrong?
Sir, because we can also have a 061, na?
Okay, fine. So if you use 6 here, you cannot use 0, 6, 1. Is it right? Hello, somebody
Yes, sir.
said. So that here
Yes,
the better way is this.
Okay,
So
okay.
so that the better way is
2, 4, 5, 6.
after 5 I can go to 1. This is path number 2. So that I can say 0, 2, 4, 5, 1. This is the path number 2. Path number 2. Is it right?
Why are we not using 6?
If you are using 6, one option you lose it. Another option possibility is this is the path. There is a path, no?
Okay, okay.
So
Okay.
that we have a path that 0, 6, 1. This is the path number 3.
6 will not be repeated.
Yeah, because 6 is not repeated. So totally how many paths is 3? I think that's the answer for that. They are using it as a 3. Hope you understand. Clear? Hello?
Yes, sir.
Now, what is my prefixed code is given? Oh, it's interesting. See, look at here. You can update the following code in the solution. See, the prefixed code is given for you, but you can edit it. In the earlier problem, you cannot edit. Am I right?
Yes, sir.
But here we can edit it. Why they are making available to edit? Can you guess it then? Why they are making it available to edit? Here also it is getting that information is widgeted and parent information. The same thing you are getting the same.
So there might be different paths in different order. Right, sir?
So here it's very simple. So whatever the parent information we got it, the parent information we are doing the backtracking and we are trying to do that similar kind of way only. But here some kind of thing we do. Just let me tell you what exactly this. So here I can update the information of this BFS list path. But anyway, what need to be updated we'll see. So what I'll do is during first time you are calling BFS, and we are getting the parent information and we are getting the level information. Is it right?
Yes, sir.
Then what you do is we try to find out a path from maybe used path from end 2 to end 1. So end 2 to end 1 used path is first one is maybe it is like 0, 3, 1. This is one used path. Is it right? Is it right?
Yes, sir.
This is called used path. What you call is this used path. If this used path, if you send it for the BFS as a parameter, next time, again you call the BFS again, you will send this user path as a parameter along with whatever parameters it is taking. I will send user path also as a parameter. Is it right? Then what I'll do is, accept this path, I can traverse other path. Is it right? Hello?
Yes, sir.
So that accept this path means other path you are getting. Other path, again what you do, again I am getting that another user path from end 2 to end 1 is another path I am getting, except this path. So maybe I'll get it, a new path is something like is it 0 to 1? No, yes, fine. So 0 to 1 means it is 0, 6,
6 and
1.
1.
So that again user path is now already updated. This path and this path is updated. Next one more time we'll run the BFS. So one more time we'll run the BFS means again we are getting that another path is that every time we try to send the used path. So this used path we are finding out using some additional code. So maybe I need to do additional parameter in the line number 3. Hope you understand. This line number 3, I need to put another parameter. The parameter might be something like a used path. Except that path, I can traverse other adjacent list. So that one, I need to use in the 16th line condition. The 16th condition is there, no? Is it right?
Yes, sir. Yes, sir.
Not visited, and it is not in the used path. Then only we'll traverse. Is it okay?
Yes, sir.
So then we'll get another parent list, another visited list, you get it. Again, we try to find out the path. So that what my suggestion is, you're supposed to build one def function which is called find path, something like a function which I'm making it as find path. Find path, what it will do is it will take the parent dictionary as a parameter from end 1 to end 2, of course, sorry. And what it will do is it is just like backtrack, whatever backtracking you have done so far, the backtracking job. Similar code, we'll write it here. And after backtracking, we'll return the list of the used path. Whatever the used path is there, that is written. So this is additional function. This is additional function. But the actual function is, I have to build, my function name is back and forth. Is it right? My function name is what? Back and forth, no? Is it right? Hello?
Yes.
Yes,
So
sir.
that I supposed to write my back and forth here, that is there, back and forth, which it has to take the 3 parameters, that is adjacency list as a parameter, and end 1 as a parameter, end 2 as a parameter. In this, we try to call BFS again and again using the find path and the used path, whatever the find path function you call it, and used path as a parameter. The used path which is returned by the find path, we send it as a parameter. So here you supposed to change additional parameter here in the 3rd line, that is used path, and 16th line you supposed to extend this if condition, that is not visited plus it is not in the used path, then only we try to traverse it. Otherwise, see, already used path is there. For example, 0 to 2, 4, 5, 1 is there. We don't want to include that 0 to 2, 4, 5 in the next session, in the next BFS traverse. So BFS we traverse again and again, excluding the used path. This is what the scenario. Just you think for a while and do it. So
Could you please open that graph?
yeah, this is my graph.
So let's say if despite of finding the 061 after the 031, if we got the other way, like 0, 2, 3, 4, and then 6 were approached.
Maybe you can. So then
So
what happened?
then,
My list is extended. Already 031 we got it. Maybe another list is added for my used path is 02451. Is it right?
yes, sir.
So my list is extended. Used path is extended every time.
So
Clear?
if like I was saying, sir, if after the 031, despite of taking 5 to 1, it get to 5, 6, and 1, then we'll miss the 061, na?
You will take that 0, 2, 4, 5, 6, and 1 you are talking about.
Yes, sir.
No, it doesn't take. After
But
going for the.
if we take that, we'll miss the 061, sir.
Wait. See, if it is 031 is over, then it will go to that. It will exclude that 031. It will go to the 02 because 2 is not used path. 4 is not used path. 5 is not used path. So that, okay, 6 and 1 might be used. You are talking about. After
Yes, sir.
reaching 5, instead of going directly 1, if it goes to 6, is that you are asking?
Yes, sir.
Let's try. I think this is the method. Definitely it works. Let's try, because used path is one preserved one which we try to use it again and again by repeated calls of BFS. Actually, in the previous algorithm, we called BFS only one time, but this time you need to call BFS again and again. Yeah.
Yes, sir.
So then only you can know. First BFS, we traverse that whatever that first BFS possible you are getting. Excluding that BFS, we try for another BFS. Clear?
Yes, sir.
So that BFS we call number of times. That's the reason they have given that updating feature of this particular BFS list. You are able to add some more parameters from this. I think it works. That's the reason. I think definitely that's the reason, because you can update the existing following solution. Use in path, we should not use it again. Maybe let's see that what happens. Whatever you said, if by mistake it went for 0, 2, 4, 5, 6, and 1, then you cannot use 0, 6, 1. Let me check it. What really happens? Yeah. Okay.
Yes, sir.
Yeah. But let's first code it. I'll give that another 15 minutes. Let's code it. If not, I'll put my logic, whatever I discussed it. I'll code it. Whether my approach is right or wrong, we'll check it. Give you the 15 minutes. I think it's okay. 9:25. 15 minutes is more enough. Yeah. My drawing is visible here. Maybe you can use it for reference. Yeah, it could be a lengthy one, maybe, but it is. Let me check my approach is right or wrong, because I don't want to make it so pending whether my particular things works or not. Yeah, my approach is, I think my approach you understood, no? Is it clear? Shall I just code it to check it?
Yes, sir.
So what I do is, because multiple things to be implemented, so let me zoom this. Yeah. So here, additionally, because they have given a chance to modify this existing code, I've given it is used path is another parameter. Maybe this used path, I don't want to use every time because BFS calls many times we are calling. So in the 15th line, what I'm doing is not visited vertex only we are visiting, of course, 16th line if condition, and additional condition, the not k in used path, because used path is a list. If already visited one, we don't visit. At the same time, it should not be in the used path. Is it clear? Both conditions you are checking. Is it clear? Hello?
Yes.
So already not visited one, we visit. At the same time, that k should not be there in the used path, because initial values of that visited is all the time it is false. Every time you are calling BFS means every time it will initialize that visited matrix, sorry, visited list is false. Is it right? Is it right?
Yes, sir.
But we use it if and only that is not there in the used path. If already used path is there in the particular vertex, we don't want to use that particular vertex in this new particular BFS. Except that we try to use other vertices. So this two lines changes we did it. I changed only adding of new parameter used path, and that one I'm checking additional condition is already used vertex. I don't want to use it again. That is what the first thing. Forget about this find path, because I'm not very much confident about find path, because find path is backtracking, which already everybody knows that. But before going for find path, I want to finish up my back and forth. Then I'll take the help of find path. Actually, find path we'll do first. Then we'll do back forth. But I'm not pretty sure about uh, what backtracking implementation I should do, which is totally different, because multiple times I need to call find path here. So that's what first I try to implement this back and forth. So here I'll use it. Used path is a empty list. Initially, first time it does not have any used path. See, they asked you to count number of unique paths. This counter is nothing but a counter. Maybe we are taking a variable called c equal to 0. Initially, my used path, first time BFS you are calling means we don't have any used path. Am I right? Hello?
Yes, sir.
So first time I'm calling. First time I'm calling means visited thing we are getting. Parent information you are getting, because it is returning two things, visited and parent. Let me call first time the BFS list path. It is taking parameters of adjacency list, sorry, adjacency list, and it is taking end one is a starting vertex which I want to traverse from which particular one starting vertex, and used path also I'm sending as a parameter. Of course, first time my used path is empty. Empty means it is free to visit the particular end to node from any vertex. Is it right? It is very free, no? First time. Is it right?
Yes, sir.
Now, so once that visiting is over, my BFS traverse is over, I will check it while my visited of end to, is it true? That means it is visited successfully. Okay. First traversal I tried with the BFS list traversal is, maybe it is traversed from 0 to 2, 2 to 4, 4 to 5, 5 to 1. Maybe I don't know. Maybe it is traversed from 0 to 2, 2 to 3, 3 is having two adjacents, maybe 3 to 1 it is traversed, maybe something like that. So once my end2 is visited means what I'll do is, it means that my counter is increasing c plus equal to 1. Sorry, plus equal to 1. Oh, sorry, it's 1. So every time my counter value I want to increase it, then I want to find out that my used path, what is there, that my path, which is that used path, what you call, So the path which is used, I want to get it. See, the find path I did not build. I don't know what should be write it later. Find path, it takes that backtracking. Backtracking we do always from parent dictionary. Is it right? Is it right? Hello?
Yes, sir.
So that
Yes,
it
sir.
takes that end1 as a parameter, end2 as a parameter. Now let me code that my find path. My find path is simple, which you already know that. It is returning simply a list, the backtracking path. The current is nothing but parent of end, because end2 to end1 I want to track it. So that end2 parent I want it, because end2 to parent again we are going to the beginning, while the current not equal to end1. Is it right? Is it right? Backtracking, no? You are tracking from end to start. Of course, end1, end2 means don't worry. It is a start node, it is end node. Is it right? Hello?
Yes, sir.
So that we are tracking from end2 to end1. So until you reach end1, this loop is repeated. In this loop, what I'm doing is just I'm appending L dot append equal to current vertex we want to append, because the parent which I have that the parent is immediately the current is updated with again parent of current, because recent one parent is updated again. Finally, you return a list. You return a list that is L. So what is this? It will return as backtracking from that ending to starting node in reverse order. We get a list, something like which you have already done it for this one, a backtracking of this, you get a list something like this, 5102, something like that. So we get the list. This particular list, I want to reuse it. This is the list which you got it. This path we got it. This I want to use it for the used path. So used path is one parameter which regularly you are setting. So what I'll do is, already used path is there, which I want to extend it, because existing list plus new list, the path we are adding, and whatever you are adding, I want to call it for the BFS list. So repeatedly I have to call it again. That is adjacency list, end one, starting from end one, and every time you call it that used path. So this loop is repeated for the second time traversal, third time traversal, fourth time traversal. So it is continuously repeated until my end2 completely it is visited, like the parent it is. So the number of times it is repeated, until my visited end2 is happened. So once that all possibilities are over, this loop is existed, that means stopped. So what I supposed to return is, I think it is a counter. Is the counter there? Yeah, this they asked you the counter. Yeah, it is counter. I think hopefully it works. Maybe I don't know. My backtracking is right. Anything wrong in this backtracking? Of course, start and then names are changed. Nothing else they get. Is the backtracking is right? Hello? Hello? Am I audible?
Yes, sir.
Yes, sir.
Yes,
So
sir.
does my backtracking is right? Because uh, this is simple thing. Instead of that start and end, they have used it as end one and end two. So even you can use start and end also, maybe, which you already familiar. So this find path, what it will do is between end two and end one backtracking, what is the path available, it will return. That path will be added to user path, except that path again one more time the BFS you are running. Is it right? Hello?
Yes, sir.
Sir,
Tell
but
me.
this user path, how we can get it from the BSF list path?
No,
Because
no.
you have,
The BFS list path is taking parameter user path. So user path initially it is empty. Is it right? First time.
yes,
So that what happens, it can have a freedom of traversing from any breadth. Is it right? First time.
okay,
So it can have a freedom of that any breadth because the user path is empty. So this condition never satisfied. Not K in user path, it not satisfied.
okay,
Yeah.
yeah, first
So
time,
that it is free. It can traverse whatever unvisited vertex it can traverse. Clear? Clear?
yes,
So once it is traversed, we get the visited and parent information. All visited is true. Parent information also updated and you will get it. Clear?
yes,
Now, is my end two is visited? Definitely it is visited. Clear?
yes.
So, but I want to know that the path from that end two to end one, what way it is visited? Because somebody said it is this one is visited through 5 or through 6 or through 3. If there is three possibilities, no? This one can be
Yes,
visited in three ways. Is it right?
yes. Yeah,
End two.
0231.
Yeah, it is possible from 3 to 1. It is
Yeah,
possible from 6 to 1. It is possible to 5 to 1.
yeah.
Is it clear? Fine. That path we are getting. That path we are getting by using find path. Is it right?
Yes, yes, got it.
So whichever path we already got it, we don't want to use it next time. So that is what user path we are sending again.
Okay, means first time it is ascending 3, second
Maybe
time,
maybe maybe someone said maybe someone said 0 to 2, 2 to 4, 4 to 5, 5 to 6, 6 to 1. This
okay.
path next time it doesn't use.
Okay, it is sending whole path or just 3 to 1 means,
No, no. Whole path means what is that one node has that only one parent. Is it right?
yes,
We are not sure this one is traversed via 3 or via 4 because BFS have the multiple BFS list. Clear?
yes,
Your algorithm after running, you will get it. Maybe you get it that this one is parent information is updated with 3 or once parent information is updated with 5. All three are correct. Is it right?
yes.
So that I want to trace out that what is the path used in the first traversal.
Sir, but
Hmm.
I have one question. That
Hmm.
BSF is used for shortest path, right? Getting the shortest path.
Hmm.
Then how come it is giving you three paths? It will give only one path, no?
Wait.
0 to 3 and
Yeah,
yeah.
yeah. You're right. You are right. You are right. Perfect. You are right. So 0 to when it is started, you have two adjacents are there, 2 and 3. They are traversed. Is it right?
Yes,
After that 2 and 3, then it might traverse from 2. It might traverse from 3. Is it right?
yes,
So that from 3 it is going maybe 1.
yes,
So that you will get it 0 to 3, 3 to 1,
yes,
or 0 to 2. No, this you will get it 0 to 3 1 only you will get it. Shortest path only you will get it. You're right. Clear?
yeah.
Hello?
Then what is the meaning of use path?
Wait. Uh, next time you are running means BFS. Again, this visited matrix and parent information is erased or not?
Yes,
Erased or not? It is erased, no?
yes, arrange.
So that when it is erased, I should not use this path 0 3 1. I should not use it. How can I exclude? Clear? How can can I exclude? Because this is an optimized path. As you said, it is BFS always will give you shortest path. This shortest path I don't want is because already used.
Yeah, but here visited and
If you are
parents, you will declare as
if you are
0.
excluded, whatever you said 0, 3, 1 is excluded. What is the next shortest one?
Okay.
What is the next shortest one? Because this condition is worked, no? Is it right?
Yeah, got it.
So that what is the next shortest one? 0 to 2,
0 to 2, 2 to
2 to
3,
4.
and 3.
Yeah,
Yeah.
3 is already used. 3 is already used.
Okay.
We cannot use 0 to 2, 2 to
2 to
4,
4 and 4 to
4 to
5.
5, 5 to 1.
Yes, got it.
Clear? Yeah. So I hope you understand. Maybe I think my approach is right. Maybe definitely it works. I think I'm sure because a lot of discussion was done. So definitely, let me run it. Is it okay? Shall I run it?
Yes, sir.
Yeah. Yeah, it is actually sorry. I have to get it every time the visited and parent information. Sorry, I did not get it. The visited information I have to get it. Parent information I have to get it because it is returning a value that's missing. Yeah. So I think first shortest one 0, 3, 1. Next shortest one is excluded with that. Yeah, it is okay. Yeah, it's perfect. Yeah, we are up to the mark. Yeah. So what happens? During first time, we are getting the shortest path from 0 to 1 is we are getting 0, 3, 1. Of course, the same list we have done it so far. Yeah, 0, 3, 1. Is it right? 0, 3, 1. No, first shortest one. The
Yes, sir.
next shortest one, which will try excluding this 3. But the rule is not applicable for 0 and 1. Again, we started from 0. We try to traverse. Maybe the next shortest one, it will try from 0, 6, 1. Maybe it is trying. Because 0, 3 already used. 3 cannot be included. 0 is having another adjacent is there 6. So it tries to go for the 0, 6, 1. After getting 0, 6, 1, 0, 3, 1 cannot be used. 0, 6, 1 cannot be used. The only way to traversal is 0, 2, 4, 5 and 1. Maybe in meanwhile, before 5, maybe 4 is having a direct connection. If it is there, it will connect to that from 4 to 1 also. Maybe, it is always it BFS goes to the shortest. Yeah, I think a private test case also it works. Let me submit. Yeah, it is okay. So the logic behind is very simple. They have given a chance of modification of this particular code. In this, every time we need to exclude already used path, and we try to investigate new BFS. That is, but whatever parent information we got at, that parent information backtracking I want to do. The backtracking will return a list. This list is called used path. So every time my used path I want to extend it. So extending. So the vertices has been extended. So initially first time you are calling means it is empty. So next time we are calling means the extended list is used for filtering. What do you call, filtering? Except that vertices we try to traverse. I think hope you got the concept. Have you understand? Hello.
Yes.
And
So a little doubt.
yeah, tell me.
So actually, how the BFS is like finding out the shortest path? Like I say before that if it will go to 5,
Yes.
6, and 1.
Yes. So
But
please,
as BFS uses the shortest approach, it goes to 5 to 1 direct.
because of the pop, no, which is the first entered one is going to be first popped one. Because of the queue. Is that okay?
Okay.
So
So
which
thank you, sir.
particular vertex is that first adjacent? For example, my adjacency list is something like this. This is my adjacency list. 0. It is having adjacents 2, 3, and 6. Clear?
Yes, sir.
So that what happens, 236 which is being pushed and popped. So maybe they are using it as queue, which is a list. List is doing append operation, so that 0 vertex which it is having 236 are adjacent. When it is popping, they are doing popping of 0. Popping of 0 means 2 is popped. For example, if this is the graph, first we are getting 0, and what is that next vertex it is going to visit?
2.
2. That's what reason of it. Maybe something like that. That
Okay, sir.
particular uh, whatever that queue they are using, that result it is removing from the front. That it makes optimization. Yeah, somebody wants to ask something. Yeah. So this is the basic yeah, I lost my yeah. The live coding session, what problems you are solving, they are very complex comparatively the OPP examination which you are getting. Because do you believe that week 4 and week 5 algorithms are very complex algorithms? Am I right? Am I right?
So
Yes,
it's
sir.
quite hard.
Hello.
Yes.
Yes, sir.
So week 4 and week 5, because week 5 still it is not started. Of course, I'm telling you, week 5 we have almost it is 5 or 6 algorithms are there, like weighted graph algorithms. So week 4 and week 5 algorithms are complex algorithms. Comparatively, that week 4 and week 5 combined of put together, we are giving one question in the OPP examination that is definitely comes from the week 4 and 5 combination. Either we give it the DFS kind of question, either we give it the weighted graph kind of algorithm, like Bellman 4 or Dijkstra's algorithm or minimum cost spanning tree, any one of it. So earlier, when that 6 terms before and 7 terms before, the PDSA OPP examination we used to give it similar kind of, because this particular problem which was there in the 2022 term, I think so, very complex problem. Later we reduced, I think even that the professor committee has reduced the complexity. They don't want to give you the very complex kind of algorithm, straightforward algorithm they want to give it. So, but what we discussed in the live coding problems is somewhat complex, like finding that length, used path. These are all different combinations. So maybe you feel difficulty in the live coding problem, but it's pretty sure the OPP examination we'll get it. The problem in the week 4 and 5 is, which is not very complex problem. That is very short. So I'm going for the third problem. Just I'll explain you the idea. So then we'll close the session. Is it okay?
Okay, sir.
Yeah.
Okay, sir.
So if we compare these live coding problems with the lead code like base, is it easy, hard, or medium? How do you rate it?
Yeah, it is. It is easy. See, actually, whatever the BFS list, all these are they're giving. Only the story they will change it. Most of the things are same. Whatever case study, what they are using is something like there is a floods are in the country. Due to that, there is a disconnection of cities. Maybe for 5 states are disconnected in the country. We want to trace out that whichever that disconnected cities in that. In that, there is one thing is connected components we are tracing. See, disconnected components is there. Do you find that there is application of DFS?
Yes, sir.
Connected components and disconnected components. You could see that. Is my screen visible?
Yes, sir.
Yeah, this is what finding connected components. So using it, these 3 states are disconnected. Something like that. They will change the story and they'll give it. So the particular core idea of the algorithm is same. We can say that that is very easy. I can say that. Whenever lead code problems or the graphs, if you are exclusively talking, only they'll change it. The story, actually what it is, the case study of it. But rest of things are same. Yeah.
Okay, sir.
Shall I go for next?
Yes, sir.
Fine. So let me go for, yeah, third problem. My screen is visible. Yeah, look at here. Yeah, it is, I think it is DFS, I think so. Let me read that. A group of workers have to complete a list of tasks. These tasks are having dependencies. So whenever dependencies of tasks are there, do you trace any kind of graph exclusively?
DAG, sir.
Exactly. Acyclic graph, which is DAG. So direct acyclic graph is there. So the direct acyclic graph means there is a dependency. One vertex is definitely dependent on another vertex. There is a directed graph which is acyclic graph. There is no cycle existed. Make sure whenever DAG is there, cycle does not exist. So make sure it is a topological sorting. Am I right? Or finding that longest route. What do you call path? But the workers prefer some interesting tasks and hate some boring tasks. You have a list of tasks the workers can do, but always workers, what they will do is they try to choose interesting tasks. They try to avoid some boring tasks. They always do most interesting one among the available tasks to be done. For example, 3 tasks are there. They try to choose one of them which they prefer based on their preference. Write a function, the cool workers. It takes that adjacency list. Adjacency list tells you the graph and the preference. So what is the worker preference? The worker, as a worker, my preference is this. So return the order of which the task will be done, which order they have to perform. Adjacency list with all dependencies it will show you, and the preference is the task sorted by preferred order, like the particular worker where he wants to prefer it. For example, if you could see this is a graph. Don't worry about this adjacency list, which you already know about that earlier problems. But here preference is given. For example, worker X has given a preference. He wants to take first priority is 1, next priority is 3, next one is second task, then 6, then 8, then 5, then 4, then 0, then 7. Last preference he has given is 7. Is it clear? Is it clear?
Yes, sir.
So here, in which the task index 0 is the most preferred one. For example, this is the preferred list. So the 0th number what he has specified. What is the 0th number is specified is 1. That means he likes to do first task as a first priority. Then the third task he wants to do a next priority. So that's what they are saying. It is 0 is the most preferred one. Keep on that index -1. Actually, index -1 means the last one. Is it right? -1 means what? Last one, no?
Last. Yes, sir.
So the last one is the least preference. That is what is order of preference. Now the situation is, before just looking and solving the problem, let me recap our topological sorting and DAG. Just I want to quickly refer what supposed to do is, this is maybe a topological graph I'm taking. Maybe 0 I'm taking is a task of 1, 2, and something like 3. So I have that 5, maybe I have 4. So I have the 7, maybe I have a 6, 8. So please make sure it is a DAG, direct acyclic. So I'm making it as this is a directed acyclic. No cycle existed. Make sure that. Maybe we are connecting this 2 here, and we are connecting this 2 to the 4 also, and 4 is connected for 3 also. So then I'll connect this 5 to 7, maybe like this. Yes. Maybe these 2 are connected. So I think no cycle is existed. Is it right? No cycle, no? Is it right?
Yes, sir.
Now let us consider our this direct acyclic graph is there. We are trying to do that. The topological sorting. See, the topological sorting means which vertex you choose it for starting of the traversal. Which vertex you choose it?
Zero.
No. Why do you choose 0?
Because of in degree 0, sir.
Exactly. First, you update that in degrees of all vertices. In degrees of all vertices. So, what is the in degree of this 0? 0.
Zero.
What is the in degree of this 1?
1.
This is 1. This is 1. What is the in degree of this 5?
2.
Yes. 2. What is the in degree of this 4?
2.
This is 1. This is 1. This is 2. Initially, whatever, no, I want to go back to our GitHub summary. I think we have a DAG here. Yeah, this is DAG. This is, your topological sorting of it. Please look at, here it is. Please look at here. Initially, in degrees are 0. And later what happened, in degrees are computed. Is it computed? Is it incremented or not? Based on the incoming vertices. From U to V, whenever U to V there is a adjacency is there, immediately in degrees updated with +1. Is it right?
Yes, sir.
So I have the in degrees. Perfect in degrees are existed. Now the issue is maybe the preference, the co-worker preference, the worker is cool worker, he has given a preference. His preference is, he said like this: 4, 3, 1, 2, 5, 0, 6, 7, 8. I think more enough. 0, 2, 8, 5. It's over. So he has given his preference is this. Can he choose 4 directly? Can he choose directly 4?
No, sir.
Why he cannot choose?
Because in degree is 2, sir.
Exactly. The dependencies has to be finished. Can he choose directly 3? No.
No, sir.
Because the dependency is there with 0. He has no choice. He must choose that first one is 0. Is it right?
Yes, sir.
So let us consider the index positions are this: 0, 1, 2, 3, 4, 5, 6, 7, 8. These are what index positions of that,
We
Hello?
we have taken this preference list randomly, right?
Yes, randomly, because the particular worker, he will give his preference, but it does not mean that his preference is definitely guaranteed. Clear? First, we try to sort out that no dependency is there, then preference will be given a choice. Clear?
Yes.
Okay. Now, so let us go for it. So as and when he asked for the 4, we cannot give the 4. So first he must do definitely the 0th one only has to perform, because there is no choice. So it has to be definitely, what is the output of this? I think the output what you are getting is, yes. So this one, it is okay. Preference list in the order in which the tasks are, yes. So the output is, he has given a preference is this, but he must finish that 0th task first. Okay, that's fine. You understand? Yeah, good. Key. So here, his preference is given, but it does not mean that the preference is definitely, it is guaranteed. So what you supposed to do is, you supposed to perform first, it is definitely the 0. You supposed to perform it, because the worker also has to perform it. No way of choosing of it. So once this is finished, these in degrees are updated with zeros. Is it right? Is it right?
Yes, sir.
Yes, sir.
In degrees 1, 2, 3 are updated with 0, because this is finished. This is finished. Clear? Now he has 3 choices. Now the worker has choices or not?
Yes, sir. 3 choices.
Yes, 3 choices.
Yes.
So out of this 1, 2, 3, his preference can be given for these 3. Is it right?
Yes, sir.
Out of that, which one is chosen first is 3. Is it right? Because this index is better, this index is next, and this index is next. Is it right?
Smaller index is chosen, sir.
Exactly. So that out of this 1, 2, 3, you have to choose first 3. Because whenever that 0 in degree is there, worker preference is given. Worker preference is 3 is first. Then what is the next preference?
It's 1.
Yes. What is the next preference?
2.
Yes, it is over. Once these are over, these in degrees will become 0. Clear? Clear?
Yes.
Yes, sir.
Out of that 4 and 5, which is performed first?
4.
Because 4 index position is 0. So that 4 is performed first. Next one, 5 is performed. That is absolute. So once these two are over, this in degrees will become 0. Whenever similar in degrees are there, like in degree of 7 is 0, in degree of 6 is 0. Out of 7 and 6, which one he has chosen? Because the worker preference is given. 6 is chosen first. Then 7 is chosen next. And finally, last one is 8. So his preference is this, but his order of doing is this. Hope you understand. Clear? Clear?
Yes, sir.
Now, what you're supposed to do is, whatever you, yeah, hello.
Sir, can you please show the map?
Yes.
Yes, sir. First, the degree of 5 will reduce to 1, then to 0, right? 1 by 1.
Wait. So let me do that again. Then it is, yes. So whatever you said is right. So, yes. Cool. So up to this, it's clear. This is okay, no? Yeah, this is
Yes,
okay.
sir.
So
Yes,
0 is definitely processed. After 0 is processed, out of that, which one is chosen? As per that, worker preference. These 3 is given a preferences. 3 is chosen. So immediately once 3 is out, this will become 1.
Okay.
Still the 4 can be chosen, no chance, no?
No, sir.
Because there is a dependency. Even worker is preferred to able to interested to do the 4th task, he cannot do it. Because its in degree is not 0. Clear?
Yes, sir. Okay.
So 3 is executed. After that, definitely has to choose 2 or 1, because he definitely will choose 1. He will choose 1. Then this one will go off. This in degree will become 1.
1.
So that this 2 is depending for these 2. So definitely he has to perform this 2. So then only this one will become 0. Okay. I think we are in right.
Okay.
You are right. Thanks for you have to recap it. No worries. Yeah. So because checking the accuracy is more important than that is. Yeah. So now out of this 4 and 5, his preference is 4, so that we should perform that 4, because both are equal 0 in degrees there. Immediately we supposed to do the preference of the worker. So preference of the worker is 4, so then 5. Out of the 7 and 6, in degree it becomes 0. This is 0, 0. So that worker preference is 6, so that it's okay. Here, what you're supposed to do is, this particular code is there, no topological sorting. This code is there. Hello.
What, sir?
This code is there. No, this is the existing code, topological code sorting.
Yes, sir. Yes, sir.
The same code you supposed to do it here. Same code. Whatever the code is there, same. Whatever it's there, same exactly. Some modifications you need to do. What is the modifications you're supposed to do? Just let me tell you. So this topological sorting, it's taking only adjacent list as a parameter. Is it right?
Yes,
The
sir.
function name you change it to co-workers, pool workers. Adjacency list is common. Preference also you send as a parameter. Clear?
Yes, sir.
Preference.
Preference.
Mm-hmm.
Because worker preference also we are sending as a parameter. Once you send as a worker preference, what you're supposed to do is this updating adjacency, in degree, all things are same. All things are same. And whatever 0th in degree is there, that is the first one executed. Is it right?
Yes. Okay, sir.
Up to
Thank
this
you.
it's clear. That up to this it's clear. No worries. Okay. And repeating of this until my queue will become empty also same. No doubt about it. Clear? Now the issue will come here. Issue will come here. So what is the issue is? What is supposed to do is there is a condition you need to check it. What is the condition you need to check it is, if in degree of any vertices, maybe in degree of this multiple vertices are there, maybe in degree of some k, this will make it available tasks. These are available tasks. Available tasks whenever many tasks are there, maybe 3 1 2 is there, there are many tasks are available because these three in degrees are zeros. Is it right?
Yes,
These
sir.
three in degrees are zeros, no? Fine.
Yes, sir.
Then what supposed to do is we supposed to do it a tuple. We supposed to make a tuple. The tuple is very simple. We supposed to make a tuple. The tuple, what it contains is list of tuples. What do you call your list of tuples? What it contains is index position and available tasks. The index position and available task. So these three are available tasks because these in degrees are 0. What is this index position of 3? 1. Is it right?
Yes, sir.
What is the index position of 1? 2. Is it right?
Yes, sir.
So what is the index position of 2?
It's 3, sir.
3.
So we make whatever available tasks are there, we make a tuple list and we want to sort it. Let me sort it. So if you sort it, what happens, if you have that in degree 0 tasks are there, 0 0 0, these tasks are sorted based on the preference. Hope you understand. Clear? Because tuple sorting means what it will do? It will take the first tuple value, no? Is it right?
Yes, sir.
So that it will sort it. Fortunately, here already sorted kind of thing you got it. Maybe sometimes what happens, these three particular vertices are having that in degrees are 0. Maybe you get it 3 2 2 1 1 3. After sorting, you get it 1 3 2 1 2 1 and then 3 2. Sorry, 3 2. Is it right? Is it right?
Yes,
So
sir.
that
Yes,
so that after sorting, then we will process this one first, then next, then next. That is only the change you need to do it. You're supposed to create a tuple as per the preference of the particular worker, if and only the in degree is having that 0. Whichever that in degree vertices are 0, you supposed to create a available task. That available task we need to create as a tuple, and that tuple you supposed to sort it. So if you do some little kind of figure out and changes of the code, you can easily work on it. But rest of the 90% of the code is very same. Same code you can copy of the topological sorting. Only arrangement you need to do is additionally you need to take it whichever available task which in degrees are 0, create a tuple, sort it, and then you pick the task and you finish it. Hope you understand. Is it clear? Is it clear?
Yes,
So
sir.
same code, except we do the change. The preference is taken as a parameter. Based on the preference, we create a tuple. That tuple will sort it. Rest of the code is same. whatever returning topological sort list, all things are same. Final topological list, what you are returning is same. But only thing is sorting job you need to do based on the preference. So hope you understand. Clear? Because same code, just you need to retype it, embedding this sorting job of tuples. Clear? That happens if and only there is in degrees multiple zeros are there. Wherever in degrees zeros are there, that vertices only we'll sort it. So here 5 and 4 is there, these two will sort it because in degrees will become 0 based on the preference sorting. Fortunately here it is okay. For example, here 5 is there, here 4 is there, then 5 will be processed first based on the preference. Is it right? Next time, is it right? So additionally, this preference data we use it because see, I think Python is having some kind of function called index. Can you check it? This index function? I don't know.
Yeah, sir, it's there.
Yeah, it is okay. I think I'm not sure about it. Index set or index. Yeah, index is there. So what happens? If any element index you want to trace out it, just I can use it. The list dot index of this 5. If I call this, what happens? It will get the index of 5. What is the index of 5?
0.
So what is
Zero.
my 5? These two I can build as a tuple. No. Here I can use index of function. Is it right?
Yes, sir.
So you can build a tuple like that. So tuple list I can build it. Then you sort it. After sorting, based on the particular tuple only, we will process that next vertex, what has to be, next task, what is to be processed in the topological sort.
So basically, sir, we can use a loop over here for making this tuple thing,
Yes,
right?
yes. There is comprehensions are there. List comprehension. You can use list comprehension, no?
Yes, sir.
I can use list comprehension like this. See. I think comprehensions, you know that simple kind of thing. Like I can create a simple list. Actually, I'm not sure about it. I think definitely we can do it. Preference is taken because preference is taken as a list, no? So preference dot index of I. Is it right? Is it right?
Yes, sir.
And I. Then it can create as a tuple, no?
Yes, sir.
For what is this I is? For I in available tasks. Is it right? Whatever available tasks. So what is this available tasks are all in degrees are 0.
0.
So this is going to be a tuple list. This tuple list we will sort it. Over. Simple. Yeah, it is pretty simple. Clear? Okay. Hello?
Yes, sir.
So this kind of simple code changes, like 2 or 3 changes, if you do it in the code, you can just whatever as per the preference only, the picking of the tasks is done. Whenever 0 in degree is there, the available tasks are updated. The available task, in that available task, we are trying to use the preference of the particular worker, which preference he has given. So the preference, you can get it lower index as higher preference. Last index is a lower preference. So for that, we try to create a sorting and then we try to process in that order. That is.
Sir, could you please elaborate the comprehension starting part?
Yeah, starting part. So again, I'll rewrite what is that. See, look at here. T is a tuple list of tuples I'm creating. So this is what preference, and preference is a parameter, This is taking index of I. So what is this I is going to be that the first value, the ith element index, whatever, that one, and value, what value it contains. Is it okay, clear? This is a
Yeah, sir, now clear.
Now, for I, where is this I is? in available tasks. What is my available task? Where in degree is 0.
0.
So this line you're supposed to write it. What is my available task says? Can you make it available tasks are? My available task is a new list. What it contains is, it can be another list. It can be considered another list, no? Is it right?
Yes.
Yes, sir.
So what is this available task is? It should be like something like K for K in my adjacent list is there. Is it right?
Yes, sir.
If I think in degree is maintained here, there is in degree.
Yes, sir. It is.
Yeah, it is in degree maintained, no? Every time in degree -1 is happening. Is it right? Okay.
Yes, sir.
So that what I'll do is, so if in degree of this K, in degree of this K is 0. Is it okay? Now my available task will get it. Is it right? Whichever that in degree 0
Yes, sir.
vertices are there, that has been considered as a available task. In that available task, we try to build a preference. Over. Simple. Both are there, sir. It's pretty simple. It's a straightforward. Only thing we have to use it comprehensions. That's it. These two lines, you put it in the same kind of topological sorting code, you will get it. Okay.
Okay, sir.
So, but in degree, all these calculations are same. See, every time appending is done means current vertex in degree is decreased. Once the edge is gone means in degree is decreased. Is it right? Hello?
Yes, sir.
Yes.
So the in degrees first update is done in this code. I don't want to change. Up to here, no changes. Only this part, 2-3 lines you have to put it. So your job is done. Okay. So this is about it. Yeah, it is pretty straightforward. Just you can check it how simply you can do. But it is very clear. Only this comprehension, sorting job, tuple, index method, just only a simple kind of figure out of this particular solution. I don't think you not write a new code also. Only thing, just you need to put that in degree kind of thing. Yeah. So I think it's clear. So any clarification, please let me know. See, one more time, I'm telling you, these are complex problems. If you could refer that last 3 terms OPP examination, problems are there, even at least recent 3 terms if you prefer it. That particular problems are moderate only. The difficulty level, we are not went for the complex. Before earlier term OPP exam questions only, we are putting in the live coding sessions. That's what the thing. Typically, all dimensions the student can understand, he can figure out the logic. That's what the objective of it. Okay. But strong recommendations before coming to the next week live coding. Please make sure you finish up that current week live coding, then only you jump to the next. Yeah, somebody wants to ask something.
Yeah, so if we see the algorithm we just like made with the sort function we use after the creating the tuple.
Exactly.
So actually, we are like playing with the complexity or not here, or we are not just
No.
considering that.
See, graph algorithms, we are not considering complexity. See, complexity is strictly considered exclusively. See, for example, let you consider OPP examination, 4 questions are there. Clear?
Okay, sir.
First question is definitely linked list, tags or queue. Just you check the early pattern of that, by professor team what they build is last since 3 terms. First question is definitely linked list, tags or queues. Clear? They don't consider complexity. Is it right?
Yes, sir.
Second question is definitely that log and complexity. Fine. Hello.
Yes, sir.
Log and complexity means definitely binary search. Is it right?
Yes, sir.
If they are using any kind of sorting method, they'll use it n log n, because that is the ultimate one. because that
Yes,
that
sir.
is quicksort. In all cases it is n log n. If it is quicksort, worst case is there, but almost they try to check it n log n only. They don't go for n square. If you try for n square by mistake, by any kind of selection sort, your second problem will fail. Time limit is exceeded. Is it right?
Yes, sir.
Third problem is definitely from the graphs, that is fourth week and fifth week. We don't consider your complexity. Is it right?
Yes, sir. Yes, sir.
And the last problem is the dynamic programming. Dynamic programming, mostly we don't consider it is complexity, because most of the dynamic programming problems are definitely n square or at least linear kind of complexity n. Is it right?
Yes, sir.
So only thing, the dynamic programming, we try to check it whether you are using efficient recursion or not. Otherwise, you are using proper tabulation and memoization you are using or not. We try to check it. Only you have to very careful about the second problem. Fine.
Yes, sir.
And one more thing I want to ask you, because anyway you are talking about complexity. The second problem is there, no? Is it right? This today's second problem.
Yes, sir.
Do you think this is less complex? Is it efficient one?
The multiple path one.
Yes.
Uh,
Is it efficient one? Second problem.
Yes, sir.
No, it's not efficient.
We are using two while loops.
Yes,
sir.
yes. Two while loops. See, one more thing. BFS you are calling
Recursive ones.
BFS you are calling one time, and this BFS is calling that, find path you are calling. Clear?
Yes, sir.
Definitely it is n square above. Am I right?
Yes, sir.
More
Sir,
than n
actually, sir, Vicky shared a part of the code for the backend forth in the chat, and that is just a two-line code, and basically it works for most of the test cases. So
Maybe I don't know, because it's efficient, but my code is not efficient, I'm sure.
no, sir, it's just returning the length of the adjacency list for the end one, end two.
Maybe he is efficient code, definitely. But thing is, graph algorithms, we don't take efficiency. Is it
Yes,
right?
sir.
See, very
Yes,
simple.
sir.
How efficiency is checked is very simple. The input we are giving is above 20,000 inputs we are giving. 30,000 inputs we give. But the graph algorithms, we don't check it with 30,000 inputs. Is it clear?
Yes, sir.
Yes.
So whenever even my particular worst implementation or Wiki's efficient implementation, they are not checking with the ideal solution. Clear?
Yes, sir.
But you should very careful about in the OPP examination, which is a log n complexity. And in the question also they will mention. So the solution must be in the log n complexity only. Is it right?
Yes, sir.
Then you should be very careful. That too,
Yes,
in the
sir.
entire OPP examination, very frequently I'm checking the pattern of that last three terms. Mostly professors are asking that the second problem is definitely log n. Just you can refer that previous term questions. Okay.
Yes, sir.
Yeah, maybe still you can try optimize it way. But graph algorithms, even I'm not good at efficient graph algorithms. Always I'll choose some standard algorithm is there. I try to implement that algorithm only. Maybe some efficient approaches are there. But in this course, graph algorithms, we don't check efficiency. That is sure. Only we check the efficiency in the sorting algorithms and searching algorithm. Okay.
Yes, sir. So, in the graded assignment of the week two, could you please go there just once?
I'm looking. Graded assignment.
So, question number 7 of the
Programming one.
graded.
Programming one.
No, sir, the graded. Non-programming, sir.
Yeah, it is graded assignment. Is it my screen is visible? Yes. Tell me.
Yes, sir. So, question number 7.
Yes.
So, actually, I selected the option number 2, but it says that it is incorrect.
See that a school wants to maintain a database of students. Each student has a unique ID and it's stored in along with other details. So the details are there. Adding a new student with a unique ID, searching for the student using their ID, and removal of the student are the frequent operations. The frequent operations they are using is adding student, setting student, removing student. These three operations they are doing. From the options below, choose the most efficient technique to store the data. Please remember, frequent operations are adding, setting, removing. Is it right?
Yes, sir.
Fine. So here, forget about this. What answer is that? So maintain a sorted list with ID. Whenever a new student is added, append the student details at the end of it, and sort the entire list using selection sort. See, once you use a selection sort, the complexity goes to that. Definitely, it is n square in any case.
Yes, sir.
Fine. That's okay. You forget about it. So whether it is efficient or not. After sorting only, we try to do setching is easy because log n complexity. Is it right?
Yes, sir.
If you setch it, then only you can remove it also. Is it right?
Yes, sir.
So one more is operation is adding. Adding means anyway, the last we add it every time, but anyway, every time you need to sort it. Yeah. Maintain a sorted list with ID. With a new student is added, whenever new student is added, append the list at end of it, sort the entire list using insertion sort. So what happens, up to 9 records, it's already sorted. 10th record, when it is added, again, it has to be resorted. Is it right?
Yes, sir.
So that again, the insertion sort also requires that n square complexity. Am I right or wrong?
Yes, sir.
If list is already sorted without any kind of issues, then it is n. That is what insertion sort. Am I right?
Yes, sir.
Fine. Now the maintain a sorted list with ID. Whenever a new student is added, append the student details at the end. Sort the list entire one with n log n. So any case, merge sort is taking n log n complexity.
Yes,
Fine.
sir.
Yes, sir.
But because of selection sort and insertion sort, they are doing appending the student at end of it. End of it means every time you need to do complete sorting. Either it is a selection sort or insertion sort. So the third one till now it looks like efficient. Let you read the fourth one also. Maintain a sorted list with ID. Whenever a new student is added, insert the student details in respect to the position in the sorted list. For example, I don't want to append at the last. I want to append it its suitable location. Is it right?
Yes, sir.
Suitable location means what is the complexity? What is the complexity?
N square.
Yes, n. Why it is n square? N only, no.
We have to just scan the list.
Then the
Yes,
list maximum it goes to that end. Maybe third element you are
But sir,
inserting. Maintain a
Sir, we
sorted is
are-
already.
List is already sorted.
List is already sorted.
Okay.
List is
Okay,
already
okay, sir.
sorted.
Okay, sir.
When see they are talking about whenever adding a new student only they are talking about. So comparatively,
Yes, sir.
n log n and n, fourth one is efficient. Okay. Yeah. Yeah. This is just only applying a simple kind of common sense and a brainstorming session. You can get it. Yeah.
Yes, sir.
Only thing the week 2 only efficiency they are accept. Yeah. Dhanvantri, you want to ask something?
Yes, sir. I have a doubt in same graded assignment. Question number 14 and 4.
Yes. First 4 we'll see. This is the 4, no?
Yes.
So here. Yes. It's a selection sort. What is the value? It's a selection sort, no?
Yes, sir.
So what is the value of 5 when the list 9, 4, 5, 2, 7, 6, 8, 1 becomes completely sorted for the first time? So first time becomes completely sorted for the first time. Yes. 9, 4. Yes. Okay. My input is taken this. Completely sorted. I don't understand what is this question.
Sir, means that's my question. Means how come it's completely first time sorted? we have to
So complete sorting means you have to run that inner loops and outer loops. Every time minimum position we are selecting and we have to sort it. What they are trying to ask, I don't know.
Sir, actually, I run this code in the Python tutor, and I found that before reaching the last one for each range in I, it gets sorted before the last position, sir. Before ending the loop, it gets sorted, sir.
No. What is I value? That's what they are asking. No? Final I value. Final I value, is it reached to that last one? That means definitely my list size is 1, 2, 3, 4, 5, 6, 7, 8, 9. Is it 9 I value?
So 5, it is 5.
Why it is 5? I don't know.
So when the I reaches 5, if you see through the Python tutor or something, so it gets sorted when the I reaches the 5, sir.
Right. First you are selecting the minimum in the list. That is 1, because minimum position is I. You are taking, and then you are finding minimum position, that is jth position is this one you are getting, and you are swapping. So that we are swapping means 1 and 9 is swapped. Is it right? Is it right?
Yes, sir.
Second
Yes,
time
sir.
you are selecting the next minimum, that is 4, 5 in this. We are selecting second minimum is 2. 2 and 4 is swapped. Is it right?
Yes, sir.
Then you are selecting 5. These 3 is selected. So that, yeah, it is okay. Understood. Yeah, actually, this swap is done only this particular condition is satisfied. Once this condition is satisfied, it is going to be swapped. After fifth position, the list is sorted. Is it right?
Yes, yes, sir.
But the loop is not stopped. Is it right?
yeah got
Yes,
it.
sir.
Understood. That's what it is. So first time when it is list started is after that I reaches to 5 only started, but it never stops. Up to that n is completed, it never stops, of course. But the list is sorted after 5 swaps only. That's over. Yeah, understood. Yeah, one more question.
14.
14. This is good. Yeah. Consider the following merge sort of the 2 sorted lists and return that 1 sorted list we are getting. Okay. So, yes. 4 sorted lists. First sorted list is 4, 5, 6, 1, 2, 3, L3 is this one, and A2 this. Yeah. Are merged into single sorted list using two-way merging in the given merge function. How many comparisons will be performed during the process? So this merge function is taking at a time 2 lists. Is it right?
Yes,
Yes,
sir.
sir.
So two-way merge means it is taking first L1, L2, then L3, L4. These two.
Yes.
First these two parameters. So here, how many comparisons will be performed between the elements during the process? Yes. So here, if you could see that comparisons between these two is 1 and 4 is merged. When it is
It
merging,
will be 6, right?
wait. Yeah, it is okay, 6. So this is 1 and 5, 1 and 4. No, split is happened, no? Is compared. Yes, until you reach it, comparison of elements, appending into the third list. The third list you are getting, okay, similar length you are getting. Whenever it is that C list is appended, otherwise B list is appended. No remaining list in these two. Yeah, it is okay. So here, definitely it is 6 comparisons. First one, two, three, because always this condition is satisfied. First list is smaller than the second list. So 1, 2, 3 is added, 4, 5, 6 is added. Is it right?
Yes, sir.
First time it is 6. This particular part of that L1, L2. Let me compare these two. 7, 9, 11, 8, 10, 12.
It
Is it
will
right?
be
Yeah. So when you do this, the comparison between that 7 and 8 is compared. 7 is smaller. So that 7,
it will be 3 only.
7,
7
then
and 8.
7 and 8 is compared. So that 7 is first. So that which is one comparison. Then 9 and 10 is compared. Then 11 and 12 is compared.
Yeah.
How do you say that is 3?
The same thing means 7 and 8 1, 9 and 10 second, and 11 and 12 third.
Oh, I don't understand. Comparisons they are asking you. How many comparisons will be performed during the process? Here the first comparison is 7 and 8 is compared. 7 is smaller. So 7 is appended. Then 8 is going to be appended. Next time 8 and 9 is compared. Is it right?
Yes.
8 is added. Then 9 and 10 is compared. 9 is added. Then 10 and 11 is compared. 11 is added. Sorry, 10 is added. Then 11 and 12 is compared. It is also 6, not 6. It's not 6. Is it 6? It's 6 comparisons. Is it right?
Yes, sir.
It is also 6 comparisons.
Yes, sir.
Now we got the list is that 1, 2, 3, 1, 2, 3,
But
4,
sir,
5.
sir, once 7 and 8 is compared, that time 7 and 8 both are append.
No. A of I is less than B of I. Immediately C is appended with 7. But 8 is still remains in L4. Is it right?
Yes.
Now L8 and 9 is compared. Next time when you are repeating.
Yes, got
Is it right?
Smaller of 2 get append, sir.
Yes. So here the second comparison is also 6. So till now it is okay. That is 1, 2, 3, 4, 5, 6 you got it. Then 7, 8,
9, 10, 11, 12.
Yeah, 9, 10, 11, 12 is another list we got it. So this is 6 and 6 elements you got it. Now 6 and 6 means how many comparisons are there? Another list of comparisons now. The same. 1 and 7, 2 and 8, something like that. So wait. Here you have to think intellectually. Comparisons are not there because this loop is not executed.
Yes.
Nowhere these conditions are satisfied. Is it right?
Yes.
Complete list of C is appended. Complete list of J is appended.
Yes.
So here already 6 plus 6 comparisons we got it. There are no comparisons further. So total comparisons are how many? 12 is there. Why it is again 14?
That's
I
the
I don't know what it is 14. Another 2 comparisons, how do you got it? Does they consider anything else there? This comparison will not be done because up to this is okay. This is a sorted list. We got 1 to 6. We sorted list. We got 7 to 12. When you compare that I and J, I less than, both of them same size. Is my I less than? No, this is not satisfied. This appending is not done. This is also not satisfied. C is not appended with B of J. Okay. So every time this I and J, is it incremented? Definitely not incremented. Because I and J will not be incremented. I less than M, J less than N. Why it is 14? I will consider this 14. Okay, 12 is okay. Another 2, how you got? Any explanation there given? I don't know. How many comparisons are performed are during this process? 2 were yes, that's okay. These 2 are merged. While this is top level merging, doesn't require this comparisons. It required, not required. Now I less than B of J. Wait. B of I contains 1. B of I contains 7. If it is less than, I'm not sure about that, how it is. Again, if it is doing every time means, again comparisons are started from 1 and 7 compared, 2 and 8 is compared. Am I right? Hello?
Yes, sir.
That again this loop is executing means what does it mean? 1 to 3, 1 to 6 is the first list, 7 to 12 is the second list. So if it is comparing, this condition is satisfied. A of that one first element is 1, B of the first element is 7. So less than that, A of 1 is smaller means C is
I
appended with.
think,
Then
sir,
what happens?
when we are
Hmm.
sir, when we are comparing with L1 and L2, that times 1 and 4 is compared. Then again 4 and 2 will be compared. Then 4 and 3 again. Means 3 multiplied by 3. It should be
Okay.
9,
Understood.
right?
Yeah, that's right. You're right.
Yeah.
4 and 1 is compared, 1 is appended. 4 and 2 is compared, 2 is appended. 4 and 3 is compared, 3 is appended. Then only 4, 5, 6 is added. So that first time only 3 comparisons. Is it right?
Yes, sir.
Correct. You are right. Next time what happens, 7, this is first tool is L1, L2 requires 3 comparisons only. Is it right?
Yes,
Yeah,
sir.
it's right, correct. So next one, 7, 9,
Yes, sir.
7, 9, 12 is there, 8 and 12 is there. So 7 and 8 is compared, so 7 is stored. Then 8 and 9 is compared, 8 is stored. So here it is 6 comparisons. Is it right?
Yes.
Yes, sir.
9 comparisons. Totally 9 is done till now. Yeah. Okay.
Yes, sir.
Now we have a list of that 1 to 6, 7 to 12. 2 lists. Because next level we are coming to the top now. Last month.
Yes, sir.
So in this, what happens? We see that. So till now 9 we ordered. Now what happens that 1 and 7 is compared. Clear?
Yes,
1
sir.
and 7 is compared, 1 is stored. Then 2 and 7 is compared, 2 is stored. Is it right?
Yes, sir.
So
The
that
6 will
is 6
do.
comparisons we got it.
Yes, sir.
6 comparisons.
Yes, sir.
In that case, it goes 15 comparisons, no? Right? I don't think something is missing. I don't know.
I think this code we have to run on the Python and
No.
increment
Maybe it's right,
while
but thing is, yeah, increment is
taking, comparing,
separate
doing the.
variable. You take it increment variable and we'll test it. Okay, anyway, I'll check this one. Huh?
Okay, sir. Thank you so much, sir.
Maybe
Yeah,
there
I
might be
will.
anomaly. Maybe 15 is the right answer. I'm sure 15 is the right answer. We'll check it. Yeah. Okay.
Yeah.
Shall we go to the session?
Thank you, sir.
Thank you, sir.
Yes, sir. Thank you so much, sir. Good night, sir.
Thank you, sir.
Good night, sir.